Linear algebra is really the study of these things called linear transformations. And so we're actually now getting into the, you might have thought we were doing the real topic, but all that was in some sense a setup, not like a that sort of setup, but setting you up to approach the main topic of linear transformations. Okay, so let's start off by defining, I'll try to give you some sense of, I'll give you the formal definition, and then I'll try to give you some sense of what these things are. Okay, so you have two vector spaces, and you have a map from one to the other. Okay, so by map, I just mean you can think of it as a function. Okay, so it takes in, this is its domain, this is its range. I don't know if you've seen this notation before, right? T is a map from this space into this space, right? This is its domain and this is its range. Okay, so it's a map from V into W, from one vector space to another. In other words, it takes a vector in V and gives you back a vector in W. Okay, it's a map from one vector space to another space. You've seen examples of this before. For example, the coordinate vector map. Remember, if you have a vector space and you have a basis, then to each vector you associate a coordinate vector, right? So that was a map from the vector space into Rn, right? That was a map from the vector space into Rn. Okay, so that's the sort of thing we're doing, right? You have a map from one vector space to another. If it satisfies these two qualities, if T of V1 plus V2 equals T of V1 plus T of V2 for all V1, V2 in V, and we're going to put vector signs on these guys, and T of alpha V1 equals alpha of TV1 for all V1 and V, and all alpha in your field, then we call T a linear transformation. Linear transformation from V to W. So this thing called a linear transformation. So if you look at these two properties, let's think about what they're saying. They're saying that if you take, so what I want to say is that this addition and this addition are two different things. Everybody look for a second. This addition and this addition are two different things, right? This addition is addition in V, right? This addition is the addition in W, right? Because here we're adding two guys in V, but TV1 is in W, TV2 is in W, right? This is a different addition from this addition, okay? And what this is saying is that the map has to have the property that it interacts well with the addition, right? It preserves the addition. The addition in V gets changed into the corresponding addition in W. And similarly, the scalar multiplication in V gets changed into scalar multiplication in W. Okay, so it gets preserved, right? It gets preserved by the map. So you can, one way that people say this is that it's sort of, that T preserves the structure of the vector space V. Right. Preserves the structure. Right. The addition in V gets turned into an addition in W. Scalar multiplication in V gets changed into scalar multiplication in W. Okay. Okay, so that's pretty abstract. Let me give you some concrete examples that will show you that you're pretty familiar with what a linear transformation is already. Okay, so it's actually nothing alien. Okay, so first off, let A be an n by n matrix. Okay, and define, let's create a map T going from Rn to Rm. Sorry, we'll call it T sub A. And create a map T sub A going from Rn to Rm by letting TA of your n vector just be AB. Okay, right? Because if you take a vector in V, I'm sorry, if you take a vector in Rn and then multiply it with your matrix on the left side, you're going to get a vector in Rm, right? That you know that, right? This guy is in Rn. Right? This is an n by 1 matrix. A is an m by n matrix, and so you're going to end up with an m by 1 matrix. In other words, a vector in Rn. Okay. Okay. So that's a map. Does it have the right properties? Does it have the desired properties? Does it have the desired properties? You tell me. Think about it for 30 seconds. 30 frantic seconds. Okay, then turn to somebody nearby and say, yeah, sure, or, huh? Okay, so let's think. Okay, so let's think, right? The first property we wanted to have is that T of V1 plus V2 should be T of V1 plus T of V2. Is that true? Is that true? Does it have that property? Well, what's T of V1? What's T of V1 plus V2? Well, that's A times V1 plus V2, right? What about, and over here we have A of V1 plus A of V2. Well, does A of V1 plus V2 equal A of V1 plus A of V2? Yes. Yes, right? So that's fine. The first property is fine, right? Right? V1 plus V2 gets mapped to T of V1 plus T of V2. Second property, TA of alpha V. Is that the same thing as alpha of TA of V? Is that true? Yes. Yes, right? A of alpha V certainly is alpha of A times V. Right? And you can pull the alpha out when you do your multiplication. Right? Okay, so this is a linear transformation. Multiplying, right? So yeah, so yes. Multiplication by matrix. A matrix is a linear transformation. And I always abbreviate transformation like this, X form and, okay. So for some reason, when I was in college, all the professors used X as an abbreviation for trans, so transformation. But after I got out of college, I never saw this anywhere else. So maybe it's just unique to that college. Okay. So this is linear transformation. So you actually have seen examples of linear transformation all along. Okay, let me give another example. Okay, we're going to make a map from R2 to R2. Okay, from R2 to R2. Here it is. x1, x2 gets mapped to x1, comma 0. Okay, x1, x2 gets mapped to, is mapped to x1, comma 0. Okay, in other words, what I'm saying here is that L of x1, x2 is x1, 0. x1, 0. Okay, so this, I'm pretty sure I haven't used this notation before. All this means is that L1 of x1, x2 is x1, 0. L1 of x1, x2 is x1, 0. Okay. Okay. So, is this a linear transformation? Is this a linear transformation? Well, we have to think, if we take the sum of two guys, x1, x2 plus y1, y2, is that the same thing as L of x1, x2 plus L of y1, y2? Right. And the second thing we have to ask is L of A x1, x2 the same thing as A of L x1, x2? Okay, so is it? Is it? Think about it for 5 seconds. Okay. Now, who thinks it is? Is it a linear transformation? Is it not a linear transformation? Maybe you need more than 5 seconds? Okay, L of x, so x1, x2 plus y1, y2, that's just going to be, this is going to be x1 plus y1, x2 plus y2, right? Right, that's how you add in R2, right? So what's L of that? L of that is going to be x1 plus y1, right? Comma 0. Right. So left-hand side is going to be x1 plus y1, comma 0. The right-hand side is going to be x1, comma 0 plus y1, comma 0. Right? Are those two the same thing? Yes. Right? Yes. Yes. Everybody okay? Anybody have questions? Close your eyes for a second. Close your eyes for a second. Am I going too slow? Raise your finger if I'm going too slow. Raise your finger if I'm going too fast. Okay, open your eyes, please. Okay, for the most part, everybody's okay. Okay, the second one here, so, right, what's alpha of x1, what's alpha times x1, x2? You take your vector and you scale it by alpha, what do you get? Somebody just say it. Devin?
Alpha x1, 0?
Yeah, it'll get this will turn out to be alpha x1, comma 0. Right? And on the right-hand side, you get alpha times x1, comma 0. And of course, there's a right? Alpha x1, comma 0 is the same as alpha times x1, comma 0. Okay, so this is a linear transformation also. Okay. Okay. Geometrically, that was algebraically. We can actually think of this geometrically. What does the L map do? L is a map from R2 to R2, right? And what does it do? It takes some guy A comma B, and what does it do to it? It gives you back A comma 0, right? So what does it do geometrically? It flattens, right? It flattens this thing down to here, right? basically like takes the shadow onto the x-axis and says, okay, I'm going to give you, this is my original guy. I'm going to project. It's what's called a projection. You project down onto the subspace here. Okay, so if you think about it that way, what we're asking here is if you have two vectors and you add them together, right? If you have two vectors, you add them together, and you take their shadow, do you get the same thing as if you took the shadow of the first guy, the shadow of the second guy, and added those together, right? And so maybe geometrically it's easier to understand, right? Certainly the shadow of the sum is going to be the sum of the shadows. The shadow of the projection is going to be the sum of the projections. Okay. Okay. So yeah, it is a linear transformation. Another thing that you could say is that we could also observe that L of AB is the same thing as 1, 0, 0, 0 times AB, right? Because that's going to give us A comma 0, right? Okay. So in other words, L is T sub A, where A is the matrix 1, 0, 0, 0. Okay, so A, this matrix, this transformation L is just one from the first category, right? We said that left multiplication by a matrix is a linear transformation, right? Well, this guy is actually just left multiplication by a matrix, right? So L is just multiplication by this matrix, right? So it's a linear transformation, right? We said left multiplication by a matrix is linear transformation. Okay. Okay. Number 3, example number 3. Let's say that we're in R2, so T goes from R2 to R2, and T of the vector V, T of the vector V, we're going to define as the rotation, the clockwise rotation of V by theta degrees. Okay, so let's call this T sub theta. Okay, T theta, right? You take some vector, maybe theta, theta is some angle. And what T theta does is it takes whatever you give it, it takes that vector and then rotates it. So here's the original guy. It's going to rotate it by theta degrees. Right? So this is going to be T theta of V. Right? This guy is V, this guy is T theta of V. So rotation by theta degrees. That's counterclockwise. Okay, so let's think, is this a linear transformation? Is this a linear transformation? If I take two vectors and I rotate them and I add them together, do I get the same thing as if I add them together and then rotate them? Right, so let's think, right? I have these two vectors. I rotate them, I have these two vectors, okay. Two vectors, I rotate them first, so I take this guy, rotate it, and then rotate this guy, and I add these guys together, right? Or I take this guy, I take this thing, and I rotate it, and I rotate it. Actually, it's the same, although my picture maybe doesn't show it so well. You get the same thing. Okay, so yeah, so this, and similarly, right, if you take your vector and scale it and then rotate it, it's the same thing as if you rotate it and then scale it, right? That one's easier to visualize, right? But they're both actually true. So this one is also a linear transformation. Yeah.
When we're doing proofs of these, can we use a geometric proof?
Well, in general, no. In general, no. But I just want to give you some idea here. Yeah, the trouble is that sometimes your geometric intuition is off. And so in math, we tend to distrust geometric proofs. Although in some fields of math, they're very geometric. So yeah, I mean, later on, yes. Okay. In fact, T sub theta corresponds to, I'm not going to explain this, but I'm just going to say it. T theta corresponds to multiplication by a matrix. By the matrix cosine theta, sine theta, negative sine theta, cosine theta. Okay. So it's also a T sub A linear transformation. So this thing also turns out to be the first type of linear transformation. It's also multiplication by matrix. Okay, so you should be starting to come up with a question at this point. What's your question? Or you should be suspecting something, that namely that
if it can be expressed as multiplication by matrix, it'll be a linear transformation.
The other way around, if it's a linear transformation, it actually comes from multiplication by matrix. Right. What you first said, we actually know already, right?
Sure.
We said that.
We proved that.
Yeah, we did that already. So, but now what we're saying is that we have this linear transformation, it corresponds to a matrix. We have another linear transformation, it corresponds to a matrix. Okay. Now I'm going to give you something that will maybe make you think that's not true. Okay. Example number 4. Let your vector space be P sub n. Polynomials, and let D denote differentiation. Is D a linear transformation? Is D a linear transformation? Does it satisfy the two properties that we want? Think about it for a minute. Okay, turn to somebody nearby, talk with them. Shake your head, nod your head.
Actually, no, for a while. Like 7 in need of coffee, but lacking the energy to get coffee.
Okay. How many people, are we going to take a poll? How many people think it is a linear transformation? How many people think it's not a linear transformation? Okay, it is. It is a linear transformation. Why? Well, if I take the derivative, what kind of properties do we need to show? That D of the sum equals the sum of these guys, right? Well, is that true, that the derivative of a sum of polynomials is the sum of the derivatives of the polynomials? Sure, right? You've seen that. Right? You have two functions, and you differentiate them. That's the same thing as you differentiate them, and then you add them together, right? Okay. Number 2, easier, even easier. Is it true that the derivative of a multiple of the polynomial is the multiple of the derivative of the polynomial? Yes, absolutely, right? The derivative of, I can pull the scalar out of a differentiation, right? The derivative of 5 cosine is 5 times the derivative of cosine, right? So yeah, this is a linear transformation. But what's the matrix? Is there a matrix corresponding to this? Not so clearly, right? Right, because you're not going to multiply your polynomial by some matrix, right? Okay, but we'll see. What we'll see in the next section is actually that we can get a matrix that represents this behavior. Okay, so the matrix, there actually is a matrix, but it's not so obvious at this point. Okay, so I hope you're getting some sense of linear transformations, right? They're maps, and they preserve the vector space operations. Okay. 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 Everybody all right? Any questions? Any questions? Okay. Basic properties of linear transformations. So these are things that that are just consequences of the definition. If T is a linear transformation, so if T is a linear transformation, then it has two properties. First off, T of the zero vector in V turns into the zero vector in W. Okay. So the zero vector gets preserved also. Okay. Second, T of negative V equals negative T of V. Right? If you take the additive inverse, you take the transformation of the additive inverse, you get the inverse of the transformed vector. Okay. So these are sort of simple consequences, and they have equally simple proofs. So here's the proof of the first one. Why is it true that the zero vector gets turned into the zero vector over here? Well, remember we have only two properties, right? We have the property that T of V1 plus V2 equals T of V1 plus T of V2, and T of alpha V equals alpha T of V. Right? Those are the only things we know about our transformation. So we have to use this. Okay. So we'll say, okay, we're going to use the second one. We see that we know T of alpha V equals alpha of T of V. Right? Well, take any V and let alpha be 0. Alpha be the zero vector. That tells us that T of 0 times V equals 0 times T of V. Right. By a property here. Right. You may remember a long time ago that we showed that 0 times V is the zero vector in your vector space, right? In any vector space, 0 times a vector is the zero vector. This is one of the sort of boring things that we showed earlier. So you get that T times the zero vector in V equals the zero vector in W. Because in any vector space, 0 times the vector equals the zero vector. second second proof. So put it up here. It's too small. Okay, proof number 2. Right, we want to show that t of negative v equals negative t of v. I say, okay, well, t of v plus t of negative v equals what? Well, so Yok is saying it's going to be 0, but we have to get to 0. So let's use property number 1. Okay, property 1, t of v plus t of negative v by property number 1 is equal to what? T of v plus negative v. Right, v plus its additive inverse. Right. Well, v plus its additive inverse is the 0 vector. Right? And we just said, by part 1, that's got to be the 0 vector in W. Okay, so we have that, right? T of v plus t of negative v is the 0 vector. Right? But we also know that t of v plus the additive inverse of t of v is the 0 vector. Right? Anybody plus its additive inverse is a 0 vector. Right? That's what additive inverses are, right? Right? This guy plus that guy is equal to 0. Right? And so what we have is that both of these left sides are equal, right? That this and this are equal, right? That t of v plus t of negative v equals t of v plus the additive inverse of t of v. Right? By cancellation, t of negative v and negative t of v are the same thing. T of negative v equals negative t of v.
You said we got by the first proof. We got a part of this?
Yeah, so this is from part 1, by part 1, right? By this,
Oh, yeah, I see.
right? We needed to use that. Yeah, read.
Why can't you just prove it by using the second property and saying alpha equals -1?
Alpha equals -1.
Oh wait, that's what we're proving. Sorry, I'm really tired.
That's okay.
You cannot prove something
Using
itself.
the second property. Oh wait.
Oh, wait.
No,
Oh, that second property.
This second. You're saying
No,
use
I am
this second.
aware.
No,
Yeah.
you're okay. You're okay. So the reason is you could do it that way, but you'd also have to you'd have to show in the meantime that negative v is actually -1 times v. Right. Okay. And I think we might have done that before. I think that's actually one of our facts from before. So yeah, actually you could do it that way.
Okay.
That would be fine. That's maybe cleaner than what we do here. Yeah. Yeah, very nice read. Okay. So yeah, you could do it that way. So just use the second fact plus this thing that we showed before. You're very awake. Good. Okay. 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 So anyway, there's some basic properties that come that follow from the definition, and they're sort of what you would like them to be. Right? That the 0 vector gets mapped to the 0 vector, the additive inverse gets mapped to the additive inverse. I don't consider this sort of thing very exciting. So if you are asleep, it makes sure that you have good taste. Although if you're awake, it's no slight of mine. Okay. Let's let me erase this. Okay. A couple more crucial ideas. So some more definitions, but these are actually pretty important. So again, you start off with your linear transformation. Okay, here's the important one. We define the kernel of T. The kernel of T is defined, so we notate it ker T. It's defined to be everything in the domain that T sends to 0. Okay. Everything in the domain that T annihilates. Okay. Everything in the domain that T sends to 0. Okay. This is basically the analog of the null space. Right? Do you remember we have the matrix, we have the null space. Null space is the stuff that the matrix left multiplication kills. Right? Right. The null space of A is the same thing as the kernel of T sub A. Right? Everything that when you get multiplied on the left side by A gets sent to 0. Okay. The second notion is something called the image. The image of T is all is everything of the form TV where V is in V. Okay, so it's the set of all outputs, right? The set of all outputs of T. Right? The set of all output vectors. Okay. I should say that in the book, they call this thing the range. They call this thing the range, but it's more typical to call this thing the image. Okay. Yeah, they have slightly different notation in the book. So what they call the image, so books definition, the image. So you have T, a map from B to W, and you have S, a subspace of B. Okay, so you have a subspace. And then they call the image of S under T is everything of the form TV where V is in S. Okay. And they denote that by T of S. Okay, so it's almost the same thing as what I'm calling the image, except that they are talking about the image of a subspace, right? And I'm talking about when people usually talk about the image, they mean the image of the whole domain space. Okay, but the book, and I don't think it uses this anywhere, but we introduce this idea, like the image of some subspace. So you look at all the outputs where the inputs are in that subspace. I don't think we really use this, so you might not need to worry about it. Anyway, this is the more common thing. Okay, so let's think a little bit about what these things are kernel and image. If we go back to number 2, example number 2, remember L was the projection on the x-axis. Then what's the kernel of L? What's the image of L? Using the common definition of image. Okay, so think for a few seconds. What's the kernel of L? Well, it's everything that will be sent to the zero vector. What's the image of L? Well, it's all the collection of all outputs of L. Okay. Talk with somebody next to you or behind you. Okay, so we have this map from R2 to R2. What gets sent to the zero vector? Everything on the y-axis, right? So the kernel of L is going to be everything of the form 0y, right? Because L times 0y is going to be 0, 0, right? And anything that got sent to 0, 0 had to be of the form 0y, right? Right? L of xy is x comma 0. Right? So you know that x has to be 0. X has to be 0. Right? So you're on the y-axis. Okay. What's the image of L? What's the image of L? Well, that's easy, right? It's just the x-axis. Right? Okay, so the image is the x-axis. The kernel is the y-axis. Okay. What about our second example? If you have the rotation, that was a third example. If we have rotation, well then what's our kernel? And what is our image? Okay, turn to somebody nearby and say, is this?
Yeah.
It's like this.
Okay. Who gets sent to the zero vector?
Transformation.
What gets rotated and turns into the zero vector? The zero vector, right? So the kernel is just the zero vector, right? What about the image? What kind of things can you get as outputs? Anything, right? You can get any vector as an output, right? Because by thinking about this vector, well, this guy will get rotated to it, right? The thing rotated theta degrees this way will get rotated theta degrees back to it, right? So all of R2 is the image. Okay. Maybe you're noticing something about the relation between the kernel and the image and their dimensions. But I'm not going to ask you about it. Number 4, differentiation on Pn. Right? What's the kernel? What gets killed by the differentiation operator? What polynomials get sent to the zero polynomial? Constants, right? So the kernel of D is all constant polynomials, right? any polynomial that's a constant. Right? What about the image of D? What about the image of D? Well, what can you get? What comes out of differentiation of polynomials of degree less than n? When you differentiate them, you're going to get Pn minus 1, right? Polynomials of degree less than n minus 1. Okay. So maybe you're noticing something, right? That this is one-dimensional, this is one-dimensional, it adds up to 2. This is 0-dimensional, this is 2-dimensional, it adds up to 2. This is one-dimensional, this is n minus 1-dimensional, and adds up to n. There's a relation between the dimensions of these spaces, and it's not a coincidence. Okay, next time we'll talk about more, we'll go more in depth to this.